Hello everybody. I just recorded your fifth video, or tried to. I went through the entire thing and it did not record. So here we go with try number two. I certainly hope that this one works because I don't feel like spending a third hour doing this. So let's go over the homework. And please remember to do your test. If you haven't done your test yet, please get on that. If you have questions, please feel free to call or email me, and I will get back to you as soon as I can. Same goes for any homework problems. If you don't understand something, don't just wait for the next tape or class. Give me a call. I'll be happy to try and get you straightened out. Chapter 3 is heavy in proof work. I told you that the other day, and it will continue to be so. The number of proofs will start to slack off as the course progresses, and we'll do more and more numerical problems as opposed to the proof type problems. But last night was all proof work, or the homework for today, or whenever you did it. So let's get over them. And we talked about a few things the other day, a couple of important ones. We talked about two very special line segments in a triangle. We talked about an altitude. An altitude is a line segment from a vertex perpendicular to the opposite side. And we talked about a median. If I told you M is the midpoint of AC, then MB is a median. It goes from a vertex to the midpoint of the opposite side. Sometimes those line segments can be the same line segment, not necessarily, however. We'll talk about special triangles today, and we're going to prove things about special triangles where they may end up being the same line segment. Since there are three vertices in a triangle, that means you have a median drawn from each vertex, and likewise an altitude drawn from each vertex. So a triangle can have three altitudes, three medians, all different lengths, perhaps all the same length. You never know. We'll see what happens as the course progresses. And we also talked about a very important property called line postulate. Line postulate said any 2 points determine a line, ray, or segment. So if M is the midpoint of AC, I could say in a proof, draw MB. As long as there's 2 points, I can always connect them. And to show that it's not already in the proof, you draw it dashed. So that indicates that you put it in there while you were doing the proof. And you would say draw MB, and your reason would be line postulate, or simply say 2 points determine a line, whichever you prefer. So you can always insert a line into a proof. It's called an auxiliary set, an auxiliary line, or an auxiliary line segment. And the reason for it would be line postulate. Line postulate. Any 2 points determine a line segment, or ray. Alrighty. Page 135, your first problem. I'm just gonna draw the figure. I'm not gonna write out all the given, etc. It's in the book. You were given circle O, GH, and J. You were given this figure, and they said you were given circle O with GJ congruent to JH. And they wanted you to prove that angle G and angle H are congruent. Angle G and angle H are congruent. You're going to learn something today in today's lesson that would make this a two-step proof. But we don't have it yet, so we're going to have to do a little bit longer proof. So one, given. And all I'm given is that these segments are congruent. Well, J is a point, O is a point. Draw OJ. line postulate. Any 2 points determine a line. Now, if you notice, I've got two triangles here, JOG, JOH. If I can prove those two triangles are congruent, then I would have corresponding parts G and H congruent. And it's easy to do because OG, OJ, and OH are all radii of the same circle, and radii are congruent. So I now have this congruent to this, congruent to that. This is fine, or you could do the following. OH and OG are congruent, and then say OJ is congruent to itself. If you want to do it that way, it is also perfectly fine. But what I've got right here gives me the two triangles, JOG congruent to triangle JOH by side, side, side. Side, common side, this was given as congruent to that. And since they are congruent, then I now have angle G congruent to angle H, which is what you were trying to prove. That is, corresponding parts of congruent triangles are congruent. And again, please remember, you can never have this before you've got triangles congruent. You can only use CPCTC when you have triangles congruent, and then you have corresponding parts congruent. This can never come before SSS or SAS or ASA. Okay? Everybody good with that one? This next one is by far the longest proof we've ever done. It will not be the longest proof we will do, but it is the longest one up to now, if you did everything right, or if you got everything in it. You were given a circle O again, and you were told that G, O, R, and this was P. You were told that NOG, I'm going to number these. 1, 2, 3, 4, 5, and 6. Anytime you have a figure where there's all sorts of stuff going on, it's a whole lot simpler a lot of times to do it this way. You were told that this big angle, angle 1, and this big angle 2 are congruent. And you're trying to prove that angle 5, you're trying to prove that RO bisects angle PRN. Well, if you notice, by the way I've got this marked, in order to prove that this angle is bisected, I need to prove that angle 5 in this figure is congruent to angle 6, I believe. Okay? So if I can get this, if I can get angle 5 congruent to angle 6, then I'm going to be in good shape. Okay? So, statement 1, all that given information. Statement 2. All right, now, you can assume straightness. Therefore, since this is straight, what do I know about 1 and 3? What do I know about 2 and 4? They're supplements. So angle 1 is the supplement of angle 3. Angle 2 is the supplement of angle 4. That's just the definition of supplementary angles. Two angles that form a straight line. And since 1 and 2 were given as congruent, then their supplements are congruent. Supplement theorem. Angle 3 is therefore congruent to angle 4. by the supplement theorem. Supplements of the same angle or congruent angles are congruent. So I've now got this angle congruent to that angle. Statement 4, ON and OP. ON is congruent to OP. They are radii of a circle, and radii are congruent. So I've got this congruent to that. Statement 5, OR is congruent to itself, reflexive. Statement 6, the triangles are congruent. Triangle, RON and ROP. By side angle side, side common angle or included angle side, SAS. And since they are congruent, then the corresponding parts, angle 5 and angle 6, are congruent by CP, and now I can make my conclusion. Since 5 and 6 are congruent, that means that big angle NRP or PRN is bisected by RO. RO bisects angle PRN by definition of angle bisect. Definition of angle bisect. You have cut it into two congruent pieces. By far the longest proof that we've done thus far. Hopefully you understood it all. In this problem, you could have rearranged your statements as long as you're like I could have put this statement 4 up here as number 2. These two statements have to be in that order. You can't put statement 3 ahead of what I've got as 2. But I could put 4 ahead of it. I could put 5 ahead of it. That wouldn't change the proof. So you can rearrange certain, if you had your proof and you had this statement up there somewhere, it will be fine. The two that you cannot flip are these two, because to use the supplement theorem, you first have to have supplementary angles. Okay? And again, notice corresponding parts has to come after you have proved triangles congruent. You must prove triangles congruent first, then you can use corresponding parts. So that's your second problem. Okay. Number 10. Number 10, the figure looked like this. W, A, B, X, Z, Y. All right, you're given a whole bunch of stuff in this one. Number 10, you're given that AZ is congruent to BZ. You were given that Z is a midpoint of XY. Now please, when you're given something like that, I'm sorry, I'm having trouble with my computer. Okay. If you are given something like this, where they tell you Z is a midpoint, don't automatically say these are congruent. You have to put that in your proof. You're told that angle 1 and angle 2 are congruent, this being 1 and this being 2. And you are told that XW, this whole side, is congruent to this whole side. XW is equal to YW. And what you were asked to prove in this problem is AW and BW. So you're asked to prove that AW is congruent to BW. All right, let's take a second here to think about this. If I could prove since this whole side and this whole side are congruent, if I could prove these little pieces are congruent, by subtraction, I could get the other two pieces congruent. So I need to prove these two little triangles congruent, and that will give me by and ax, and then I can subtract them from the bigger one. 1 given. 2, you were told z is a midpoint. I said you've got to insert that in your proof. Now I can say xz is congruent to yz. Definition of bisect. A line segment is bisected if it's cut into two congruent pieces. Statement 3. These two little triangles are now congruent. Side angle side, side angle side. So the two little triangles, triangle ZAX, is congruent to triangle ZBY. By SAS, since they are congruent, that makes AX congruent to BY, corresponding parts. And then by subtraction, I now have this little piece congruent to that little piece. The whole piece is congruent to that whole piece. By subtraction, AW is now congruent to BW. By subtraction, SUBT, or use the negative symbol. And bada boom, bada bing, we are done. Hopefully we're still recording. Let me check. Yes, okay. Okie dokie. That was page 135. Now on page 140. And 140, we talked about overlapping triangles. And anytime you have a figure that has triangles that overlap other triangles, I told you it sometimes will be to your advantage to actually pull the triangles out that you're trying to work with. You don't have to do it, but sometimes it will make the problem a little bit more clear if you actually pull things apart. You don't have to do it, but it sometimes will be it's nice to have a visual aid. So, number 4 on page 140, you started with this. ABC. You were given this figure, and you're told that 1, 2, 3, 4. Angle 1 is congruent to 3, and angle 2 is congruent to angle 4. And they ask you to prove that, or they use the word conclusion. Please remember the word conclusion or conclude is the same as prove or proof. It's a 2-column deductive proof. The word find, which we'll get more of as the course goes on, is a numerical problem. This is a deductive proof. They wanted you to prove that BC, they wanted you to prove that BC is congruent to DE. All right, here I've got a bunch of triangles. I've got a whole bunch of triangles in this figure. It might be to your advantage to pull them apart if it helps. And hopefully you recognize, I'm trying to prove BC and ED, well, they are corresponding parts of the following two triangles. And again, if you do pull them apart, they don't have to be to scale. They're just a visual aid. Just label them CD, CD, E, and B. Here are the two triangles. This bottom triangle, CDB and CDE. And what I'm given is angle 2 is angle ECD. ECD is right here, 2. Angle CDB is what was labeled as 4. So I know right off the bat those two are congruent. And hopefully you recognize CD is the same in both of these triangles. So now all I've got to do, if I can get this big angle, BCD, and this big angle, EDC, congruent, the two triangles are congruent, and voila, we've got what we need. We can have corresponding parts. And hopefully you recognize the addition property. One given. All that info that was given is now entered into the proof. Statement 2, and this doesn't have to be your statement. It could be something else. I'm going to just do it this way. Reflexive. And then, since 1 and 2, 3 and 4 added together will give me the same measure, I can say that angle BCD, please don't talk about angle C, because in the original figure, not the way I pulled it out, angle C is different, so don't say that. Angle BCD is congruent to angle EDC by addition, or use the plus sign. And I can now say the two triangles are congruent. Triangle BCD is congruent to triangle EDC by, we just said those are congruent by addition. Therefore, these two triangles are congruent by angle, side angle, ASA. And since they're congruent, then corresponding parts are congruent, making BC congruent to ED. By CPCTC. Again, we have got this follows triangles congruent. You can never have triangles use CPCTC before you have proven that triangles are congruent. So bada boom, bada bing. That's number 4. Okay, number 7. Number 7, you're given this 5-sided figure, pentagon, and they tell you that it's equilateral, and they defined what equilateral meant for you. An equilateral figure is a figure in which all sides are the same measure. So this was P O So you're given that this 5-sided figure is equilateral. NOPRS is equilateral. And they also told you that angle OPR, this big angle, is congruent to that big angle. And they told you that PT, this little piece, and that little piece are congruent. And they wanted you to prove that OT is congruent to ST. All right, now, again, you got a lot of overlapping triangles in this figure, and hopefully you saw this. If I could prove this whole line segment is congruent to that whole line segment, OR and SP, since these little pieces are congruent, if I subtract that piece from OR and that piece from SP, then the remainders, ST and OT, would be congruent. And that's what you're trying to prove. So the two triangles I want to work with here are ORP and triangle SRP. And what I know is that's congruent to that. And I'm only given a part of, I can't mark it on here. This piece is not in these figures yet. But if I could prove these two triangles congruent, I can get the whole line segment OR and the whole line segment SP congruent, and then by subtraction, get the remainders congruent. All right, you were told that the original five-sided figure was equilateral. Equilateral means all sides congruent. Therefore, I know OP, PR, and SR are all congruent. OP is congruent to OR, is congruent to RS. Definition of equilateral. So I've got this congruent to this, that, and that. The triangles are congruent. Now I've got triangle OPR congruent to triangle SRP. Side, angle, side. Side, angle, side, side, angle, side. And since they are congruent, then the whole segment, OR, is congruent to SP. CP, CTC. They are corresponding parts of congruent triangles. Now, since this whole segment and that whole segment are congruent, by subtraction, when you subtract this little piece from OR, you'll get the same thing as when you take this one, SP, and subtract TP, and what will be left is what you were trying to prove. This segment minus that is OT. This segment minus that is ST. So OT is congruent to ST, and you're done. Subtraction, SUBT, or use the negative symbol. And we are finished. Hopefully you see that one. Okay. Everybody good? All right. Hopefully you're catching on. Proofs are not easy, but as you do more and more of them, things will fall into place. And as we get more and more information, a lot of these earlier proofs they'll be even simpler than they are right now, because we're going to learn things that are going to make it even quicker. The more info you have, the more ways you have of attacking a proof. The last one on this homework set was number 9. And number 9, you're given the figure. It looks like this. AWX. Z, 5 and 6. All right, in this figure you are given that YW bisects AX. And again, don't just automatically mark these as congruent. You have to insert it in the proof. The definition of bisect tells me that it's cut into 2 equal pieces. That has to go in the proof. And you're told that angle A is congruent to angle X. And you're told that angle 5 is congruent to angle 6. And they wanted you to prove that ZY, or ZW, is congruent to YW. Hopefully you see the 2 triangles you're going to work with here. Triangle ZWX and YWA. And again, I'm going to just pull them out. It's not necessary, you don't have to, but a lot of times it makes it easier to see what you're trying to get to. XYZ, and this one is YWA. If I could prove these 2 triangles congruent, then I would get the pieces YW and ZW congruent by corresponding parts of congruent triangles. And what I'm told is, I know that's equal to that, X and A, and you were told that W bisects AX, so I'm going to be able to get these congruent. If I can get these big angles congruent, I'm done. So let's do the following. Let's call that 1. All right, given. Statement 2. Because this is bisected, I know AW, and again, you have to put this into proof. AW is congruent to XW. That's the definition of bisect. Statement 3. Angle 1 is congruent to itself. Reflexive. Anything is congruent to itself. Reflexive property. Since 5 and 6 are congruent, 1 plus 5 and 1 plus 6 are going to give you the same value. So by addition property, the big angle, AWY, is congruent to the other big angle, XWZ. Addition. It gives me this and this. Are these two triangles now congruent? Angle, side angle, angle, side angle. So triangle AWY is congruent to triangle XWZ by ASA, making YW congruent to ZW, CPCTC. Corresponding parts of congruent triangles are congruent. Bada boom, bada bing. Hopefully you see that now. Okay. So that is it for the last night's homework. Again, if you didn't follow any of that at all, rerun it, see if it helps. And if you still have questions, jot them down. I'll be happy to answer them on Friday, or call me or email me. Okay.